Hi, everybody. Welcome to this webinar. So we're just going to leave a few more moments just for a few more people to join, and then we'll get cracking today. So it looks to there's 3 people who are joining today, so that's great to see. So hi, everybody. Welcome to the final instalment of our immunoassay week. For those of you who have seen some of the webinars that we've put on this week, welcome back. And for those of you who are new, welcome. Hi, my name is Dr. Amy Turner, and I am the Scientific Marketing Specialist here at Proteintech. And today I'll be delivering this workshop, running through everything Western blot, what they are, how they're performed, and how to troubleshoot from basics to advanced. I've also got Callie Anderson on the call with me today. She'll be really happy to answer any questions that you've got. So if you just pop those in the chat, we can answer as many as possible during today's session. And we will have a short period of time at the end just to do a short Q&A. So briefly, before we get our teeth into the Western blotting protocol, I just wanted to give a brief overview of Proteintech. So what we produce and what our core values are. So Proteintech is a leading manufacturer of antibodies, bioactive proteins, and immunoassays across multiple different research areas. And our portfolio comprises 3 core product lines. So number 1 is Proteintech. So Proteintech has been the original manufacturer of antibodies and immunoassay kits since 2002. And we have antibodies against over 13,000 human targets, with the future aim to have a binding reagent for each and every protein of the human proteome. We acquired Chromatech in 2020, meaning our portfolio now spans into high-quality nanobody research reagents, including the market-leading GFP trap for all your immunoprecipitation needs. And finally, we have our humankind portfolio, which is made up of bioactive proteins, for example, cytokines and growth factors. And these product lines are ISO accredited, meaning we can manufacture GMP-grade recombinant proteins for use in cell and gene therapies. Now, these 3 product lines share common values under the main Proteintech brand, i.e. we manufacture in-house, we have really high quality validation, but they all address our customers in separate and specialized manners. So as a company, we measure our success by your scientific success, specifically helping you publish impactful research faster. So our products are featuring in more and more publications each year. And actually, as of today, we have over 200,000 citations worldwide. And that number is growing really, really fast, helping us to reach the top 10 antibody companies with regards to citations. And now for the science. So today we're going to be looking at the theory of a Western blot workflow, hopefully gaining a greater understanding of how modulation of each step can affect your results, and also gaining further insights into the biochemistry that is happening during your workflow. We'll then take it a step further, learning how to tailor a Western blot to those hardest to deal with proteins that we all know and love. And that will comprise slides determining the best course of action for large proteins, small proteins, and phospholipid-related proteins. Now, I'll end today's session outlining the common troubleshooting problems that researchers have and the advice that Proteintech can offer to help you solve those issues. So like I said, I'll just give you a brief overview of the workflow and then we'll go into a bit more detail. So what is the purpose of a Western blot? What is it? Like I said, this is from basics to advanced. So hopefully we've got some people here who are quite new to the protocol, and some of you might be a bit more well established. So a Western blot, also known as a protein immunoblot, is a laboratory technique used to detect and analyze specific proteins within a complex mixture. It's based on the principles of electrophoresis, immunodetection, and protein blotting, and is a fundamental tool in molecular biology, cell biology, and biochemistry. So on the slide there, I have listed some of the most common investigative applications of a Western blot. So we've got expression analysis. So most people could use a Western blot to estimate the relative protein abundance between samples, e.g. between proteins of a healthy and diseased state. We can also use Western blot to look at post-translational modification analysis, so looking at phosphorylation of your protein, glycosylation, ubiquitination, that sort of thing. And these are really popular for people who are looking at cell signaling analysis. We can also use Western blots to look at protein localization. So you can actually fractionate your sample, your tissue, or your cell lysate into subcellular fractions, which enables you to determine where your protein of interest actually localizes within a cell, and you can look at that between different variables. Finally, the one that I've listed on the slide there, and there are many more applications of a Western, but you can look at confirming protein-protein interactions, for example, after performing a co-immunoprecipitation. So now you know what the what is, I can now talk you through the how. So on the slide, you'll see the protocol overview of a Western blot. So before any Western blot, you will prepare your sample. And for the purpose of this workshop, that sample is going to be a cell lysate, which is a complex mixture of endogenous proteins prepared through solubilizing a cell sample of the researcher's choosing. So once the sample is prepared, the protein mixture is separated based on size using SDS polyacrylamide gel electrophoresis. And after this size separation, the proteins are then electrophoretically transferred onto a solid support, such as a nitrocellulose membrane or a PBDF membrane. So once on the membrane, you can then incubate your protein with protein-specific antibodies that bind to the target of interest. And these antibodies can typically be tagged with an enzyme or fluorescent dye, which then enables you to detect your protein of interest on that membrane. So, like I said, I'm going to go through each detail of the protocol in a little bit more detail for you. So step one, sample preparation. So like I said, we're going to be looking at cell lysates. So lysate preparation can be whole cell or subcellular fractions to enrich proteins, and the preparation of the sample lysate is really crucial to the success of many assays, not just Western blot, but ideally throughout the whole process of sample preparation, from lysate collection to analysis, your protein of interest, you would hope, will be really well preserved and protected from the activities of things like proteases and phosphatases. So proper storage and handling of your lysate are really crucial to avoid any of that degradation. So for successful electrophoretic separation, proteins must be well solubilized. And solubilization is the process of breaking down interactions involved in protein aggregation, which include things like disulfide bonds, hydrogen bonds, van der Waals forces, ionic interactions, and hydrophobic interactions. So if these interactions are not prevented, proteins can actually aggregate or precipitate, which will result in artifacts or sample loss, which is not what you want when you're running a Western blot. So a successful cell lysate preparation is really founded in the lysis solution, which is made up of 5 main components, and you can tailor each of these components to the needs of your protein of interest. So the first thing that you should consider is the buffer system, which is used to maintain the physiological pH of the solution, which is critical to ensure the protein stability and prevent any precipitation of the protein. So what you want is to essentially mimic what that protein would be experiencing within the cell. So you want to generate an environment that is very similar to the cell. So we typically recommend using tris HCl-based buffers, which also help prevent the formation of insoluble products with other ions. And the buffer system that you choose for your lysis will kind of depend on where your protein of interest will reside within the cell. So every protein is different, and you should really read the literature before proceeding with your protocol. So have a look at where your protein is within your cell and tailor your buffering system to that. The second component of a cell lysis that I want to talk about today is the salt ions. So anything from sodium chloride, potassium chloride, these things are added to the solution to maintain the ionic strength and can also help to disrupt cell membranes and molecular interactions. It is worth noting here that if the salt concentration is too high, then proteins may actually precipitate. And if you've ever seen smiley bands on your Western, then this is potentially why. So if you've seen smiley bands, just have a look at your salt concentration. If it's too high, just knock it down a few factors. Thirdly, what I've listed there is the chaotropic agents and detergents, which are added to your lysis solution to weaken hydrophobicity of proteins and lipids, disrupting hydrogen bonds, and reduce the stability of the native state. So detergents are surfactant compounds that denature proteins by solubilizing the hydrophobic groups, and they're really, really important in any lysis solution. The addition of protease and phosphatase inhibitors are super important in a Western blot, especially if you're looking at phosphorylated proteins, as these inhibitors can act to inactivate or block the activity of these proteases. And there are several different classes of phosphatase and protease inhibitors. And here at Proteintech, we would recommend using a cocktail of a few. Finally, what I've listed on the slide there is reducing agents. So reducing agents are really important to disrupt disulfide bonds, to denature proteins from multimeric or 3D structures. So thiol reducing agents such as beta-mercaptoethanol or DTT should be added to your lysis solution just to really disrupt those intra and intermolecular disulfide bonds and can achieve a really complete protein unfolding state of your lysis solution, your sample. So moving on, well, actually not moving on too much. So what we want from this slide is to really hammer home that your lysis solutions should be really, really optimal before you start any Western blot. So top tips from Proteintech are to use the Reaper buffer. And we find that time and time again, this performs best. If your samples are proving hard to solubilize with the components of the lysis buffer that I've previously outlined, then do try a sonication step to really help break up those tough cellular interactions. Always keep your samples on ice. This is pretty common among most molecular biology techniques, but what you want here is to reduce the thermal cycles that can potentially cause protein degradation and reduce catalysis by proteolytic enzymes. Again, just hammering home here that the use of phosphatase inhibitors and protease inhibitors is really recommended just to maintain your protein of interest in its most useful state for your Western blot. So for more information about the lysis workflow, please head over to our Proteintech ECR hub. We actually have a full webinar dedicated to lysate preparation, actually led by Callie, who's on the call with me today. So if you do want any more information, just head over to that hub. So once you've got your lysate prepared, you actually, before running your STS page, you would like to combine this with a sample buffer which is sort of tailored towards your STS page. So the STS in the sample buffer is an ionic detergent, which has a negative charge. And in addition of this to your samples actually coats these linearized proteins with a negative charge proportional to their length. And what this does is it allows the separation of your proteins by size on application of the electrical current that you'll run during your STS page. You would also, at this point, add glycerol to your samples. So I know when I've been running many Western blots during my PhD that if I loaded my samples onto my STS page gel, I sometimes would see my samples float up over the gel and I'd lose them and it was never a good day. So the way to avoid this is to actually add glycerol into your sample buffer. And what this does is it increases the density of your sample so that it doesn't float away and it remains in your gel ready to be separated. Bromophenol blue is, as the name suggests, a blue compound, which is purely added to your samples for visualization. So you want to have your samples be blue like this so that you can see them running through your gel and you know at what point to stop that STS page. And finally, again, within your STS sample buffer, you always want to keep that reducing agent in there just to maintain the denatured state of your protein. So at this point, you're going to have a lysate with your STS sample buffer in it. And prior to running the STS page gel, most protocols will tell you to heat your sample for about 5 to 10 minutes at 95 degrees. And what this does is the heat increases the kinetic energy and causes the molecules to vibrate rapidly. Again, just disrupting those hydrogen bonds and making sure that your protein is in its most denatured state. Like I said, this is a very common practice, but of note is if you're working with a membrane protein, heating the sample actually might not be the best course of action. So on the screen there, I have listed a sodium potassium chloride co-transporter, which is a membrane protein. And as you can see, when you boil this sample, you actually get no signal in your Western blot. And this is because membrane proteins are notoriously sticky proteins. And when you add heat to them, they can actually aggregate and cause these precipitates, which when you try and run your STS gel, they clog up the top of the membrane, the gel, and therefore they won't migrate through and therefore won't be transferred onto your membrane and you won't get a signal. So some tips how to prevent this. is actually if you're working with a membrane protein, just trial a few different gradients of temperature. We recommend from 4 degrees all the way up to 100. And as you can see on this gel, this membrane is actually an ATP transporter, again, another membrane transporter. And all these different samples have been treated with a different temperature. As you can see, as you increase the temperature, the quality of the blot actually decreases. And this is because you can see this aggregation of the protein upon boiling. So you don't need to have the boiling step for membrane proteins, but what you can also do is add a cheotropic agent such as urea, and that can sometimes help to prevent this protein aggregation. Of note, if you are going to use urea in your samples, don't heat above 37 degrees because urea can actually hydrolyze and modify the amino groups on your proteins, so just be aware of that. Okay, so that's your sample preparation. We're going to talk to you about STS page now, which is a fundamental technique for protein separation and analysis, and understanding the principles and proper execution is really crucial for your experiments. So in essence, STS page is a polyacrylamide matrix with pores that your protein will migrate through at differing speeds according to their size. So STS in the sample buffer and running buffer of your experimental setup will coat your protein with a uniform negative charge so that they can be separated by size upon this addition of the electric current, i.e. the smaller the sample, the faster that they will migrate. So it's really important to take note here of the expected molecular weight of your protein, as the optimal acrylamide percentage in your gel will vary dependent on the size of the target protein you want to separate and analyze. So different gel percentages are used to resolve your proteins. And what I've done on the screen there is actually give you the recommended acrylamide percentages based on your molecular weight of your protein. Now, as well as tailoring your gel percentage to account for your protein's molecular weight, we also recommend loading sufficient protein sample. And our go-to is loading 30 micrograms of your lysate prep to optimize the signal-to-noise ratio with regard to non-specific binding. So on the plot here, you'll see that as you increase the antigen amount that you load, the non-specific binding of your antibody actually increases linearly. So what we want to do is actually load enough protein such that the specific binding, which is the blue line here, is actually above the non-specific binding. So the area under the curve is as big as possible for the greatest signal detection. So if you haven't already planned your experimental controls at this stage, you really should think about what samples to run as you begin the gel electrophoresis. And at the bare minimum, a protein ladder is required to validate the expected molecular weight of your protein. So here at Proteintech, we supply both standard and broad range pre-stained protein markers. And they're really great for both Kamasi staining and also Western blotting. So protein markers are not only useful to determine the molecular weight of the proteins in your sample, but you can also use them as a quality control service. So they ensure that your gel and your electrophoresis apparatus are functioning as you want, and because any anomalies in the ladder migration pattern can actually alert you to potential issues in both the STS page and also the transfer step. So in order to troubleshoot issues with your lysate preparation, and your STS page gel prior to performing your Western blot, we recommend doing a Kamasi staining. So Kamasi stains both hydrophobic and basic amino acids, and it gives basically all of the proteins in your sample this blue stain against this really clear background. And what that does is it shows that your lysate preparation worked, you've solubilized your proteins, and your gel has run well. You can use both Kamasi and silver stain, but we recommend using Kamasi because it's super simple and it's also reversible. So we've got a optimized lysate preparation. We've optimized the STS sample, the STS page, sorry. The next step of a Western is to do the transfer. So the choice of transfer method depends on the specific experiment and the need for efficiency, speed, or resolution. Now, both wet and semi-dry methods work on the principle that the negatively charged proteins will transfer out of the acrylamide matrix and adsorb onto a solid membrane when electric current is passed through the setup. And this not only maintains your protein integrity, but also allows antibody recognition and protein detection. So shown on the slide here are the key differences between the two main protein transfer methodologies. Like I said, wet and semi-dry transfer. So wet transfer is the traditional but slower and better for larger proteins. It comprises the STS page gel and a transfer buffer soaked membrane sandwiched between two blotting pads, and they are submerged in a tank akin to the STS page setup. The tank is then filled with transfer buffer, allowing the facilitation of the proteins to move from the gel to the membrane. It's quite similar to the semi-dry transfer. However, the semi-dry transfer is essentially in a specialist transfer machine, and it is not surrounded by the buffer. It is just between two cassettes, which facilitate the electric current. So something that I didn't know when I was doing my PhD, and I really probably should have, is that you really should think about the membrane that you use to transfer your proteins onto. So PVDF and nitrocellulose membranes bind to proteins using different interactions, with the nitrocellulose using hydrophilic and electrostatic interactions, and the PVDF using hydrophobic and dipole interactions. So we tend to recommend the PVDF membrane, as actually 80% of antibodies use hydrophilic and charged interactions when they bind to their protein target. So when you use a nitrocellulose membrane that also uses these interactions, then they can actually mask the antibody binding site, which means your target signal will be a lot weaker. Another reason that we tend to recommend the PVDF is that it has a higher sensitivity and higher durability, which means it can be probed and then stripped and then reblotted a lot more often. But just another point to note when optimizing your transfer steps is the pore size of the membrane. So be aware that different sized proteins will be more suited to different pore sizes. So you don't want to be using a really large pore size when you're looking at a tiny protein, because it might just transfer straight through the membrane. Okie dokie. So at this point in the protocol, you will have your precious protein immobilized onto a solid support membrane, which now needs to be blocked prior to antibody staining. And in this section, I will also discuss the importance of stringent washing. So why do we block our membranes? So background signal is unfortunately just a consequence of biochemistry, and therefore blocking is a really critical step in a Western blot. So the blocking step essentially treats the membrane with non-specific proteins, such as that within non-fat milk or bovine serum albumin. And these non-specific proteins cover the remaining protein binding sites that are not occupied by your protein sample. And this essentially prevents non-specific binding of your antibody and reduces background noise. So the choice of blocking agent really depends on the specific requirement of your experiment. And for example, you wouldn't want to use milk-based reagents if you were looking at the biotinylation status of a protein. And this is because non-fat milk actually contains endogenous biotin, which could lead to competitive binding. So you can use alternatives such as BSA reagent, which are great if you're looking at biotinylation or streptavidin-based detection methods. Having said that, Proteintech actually recommend the use of non-fat milk blocking reagents as the standard workhorse with sort of internal testing showing overall that it actually performs better than BSA. And it's the most widely used reagent, and it's really cost effective for our customers. Having said that, all of our Proteintech products actually come with product-specific protocols that outline the most appropriate blocking conditions for your antibody of choice. So if you do encounter issues with your Western blot results, you can actually tweak the blocking step with just a few small tweaks that could really optimize your results. So the first one would be longer incubations. And second one is actually increasing the concentration of your reagent. So rather than using 5% milk, you can go up to 7% milk. And this would hopefully result in a lower background. But as with quite a lot of science and most experimental protocols, it's always a balancing act. So you don't want to overblot, because that actually might lower your target signal. Next slide, there we go. So as I said, I'll just be talking you through the washing step here. So the washing step in a Western blot is probably the most critical factor, although arguably one of the slightly less interesting ones, but it's a critical factor in removing the unbound or non-specifically bound antibodies and other reagents, so it helps to decrease background again. And if you're struggling with issues with background, the wash step is probably the first point of call to try and troubleshoot this with some, again, very simple steps. So firstly, you could increase your washing time. So you could do 10 minutes times 3, or increase the frequency of your washes. So you could do 5 minutes times 5. But do be careful not to overwash. Again, you need this balancing act. You don't want to remove any of your pressure sample, but you also want to get rid of the background as much as possible. Secondly, always use fresh buffer for each wash, and you can also increase the volume of the wash buffer that you add to the membrane at each step, and this can help to really reduce that background and enhance your signal. So lastly, detergent. Tween 20 is the most commonly used non-ionic surfactant, which means it is comprised of both a hydrophilic head group and a hydrophobic tail. And what this does is it allows the buffer to interact with both hydrophobic and hydrophilic molecules, meaning that it can help wash away those tough, sticky proteins that are non-specifically binding to your membrane. So just have a think about how much tween you add into your wash buffer. So the standard protocol is 0.5%, but you can increase this if you are really struggling. So once you've blocked your membrane, now's the time for the antibody steps, which are really the bread and butter of a Western blot. So primary antibodies facilitate the specific detection of your target protein, and it is at this stage where you should put a lot of effort into optimizing your results and incorporate adequate controls. So choosing the right antibody is really paramount for understanding the success of your results. So I'm just going to use this slide to refresh the different types of primary antibody and why you might choose one over the other. I do apologize if you have joined us for this week's immunoassays. You may have seen this slide before, but it's always good to have a bit of a revision. So polyclonal antibodies are purified from the sera of host species. And in the case of Proteintech, that is a rabbit who has been exposed to a specific whole protein immunogen. Now, as the name suggests, once purified, these polyclonal IgG antibodies will recognize multiple epitopes on the given immunogen. And that means what you have is a really high affinity antibody, an antibody mixture that is really great for detecting proteins from rare species, for example. So as you can imagine, having multiple recognized epitopes actually increases the chance that the rare species homology would be cross-reactive. Unfortunately, polyclonals are sometimes prone to some lot-to-lot variability, and that's just because of their purification methodology. So not every rabbit will produce the same ratio of IgGs at all times, which is where monoclonal and recombinant antibodies are really great. So because they have a slightly different purification and production methodology, so for example, monoclonals, once they've been raised in their host species, the B cell clone that generates that IgG is then transformed into a hybridoma that continues to grow and produce the antibody of interest without the need to re-immunize the mouse or rabbit, which means that the lot-to-lot variability are a lot less. Again, as the name suggests, single epitopes are recognized with a monoclonal antibody as opposed to the polyclonals. And let me just talk to you about the recombinants as well. So the recombinant antibodies, these are antibodies whose IgG has been taken from an immunized animal and in vitro cloned into a really simple recombinant expression system, which actually means that they have incredibly low lot-to-lot variability and are really great for long-term projects. So I can't talk you through a Western blot workshop without emphasizing the importance of controls, antibody controls specifically. So these controls ensure your results are biologically real and you're not misinterpreting artifacts or background as real signal. So the workhorse control of a Western blot will always be the loading control, which is sort of a benchmark, something that should not change despite other variables in your experiment. It should be something that's ubiquitous and something that's really highly expressed. So for the most part, these are structural and metabolic proteins, such as those listed on the slide. So I've used the example of Proteintech's GAPDH antibody there. So as you can see, really clearly expressed here. And this is actually the #1 cited of its kind. What I would say here is to be careful of the housekeeping gene that you do choose in your experiments. You really want the protein to be appropriate for the protein that you're actually interested in. So for example, if you're looking at a mitochondrial marker, a good control housekeeping gene would be the COX-4, which is also a highly featured product of the Proteintech offering. So moving on to other common controls that people may or may not think about. So observing protein phosphorylation is essential in many cell signaling experiments, but quantifying the amount of phosphorylated protein requires an understanding of how much of the total protein, both unphosphorylated and phosphorylated, there is within a cell. So you should always consider that when you choose your primary antibodies. So always use a phospho-specific and a total protein antibody. So as we're talking about the primary antibody section of a Western blot, you can also think about doing a no primary antibody control, which checks the specificity of your secondary antibody. So moving on, this is my second slide on controls. You can tell that I'm trying to make everybody a good scientist here. So you've also got your positive and negative biological controls, and these will depend, again, on your experiment and your research area, but they're really vital to validate your results. So an example of a negative control is a cell line that is known to not express your protein of interest, with the opposite positive control being a cell line that is known to express or overexpress your protein of interest. So you're really confirming the specificity of the primary antibody you are using for your Western. And what I will say at this point is it's great to check the literature. Have a look what others have done in your area, because you really want your controls to essentially reflect what else is being done in the research area so that you can directly compare. Also have a look at your antibody supplier, see if they've used controls, and really be critical before you purchase an antibody. So on the slide here, I've actually given an example of an interleukin, which acts as a really great positive control and negative control. So this is an inflammatory marker. It exists in a specific subset of tissues, including the small intestine and the colon, but it's known to not be expressed in the spleen. So this is a really great control. And as you can see, this interleukin antibody picks up the signal in the expressing cell lines, but you can see an absence of the signal in the spleen, which is what you'd want to see. So we've now spoken about the primary antibody. After this, you would then do a wash step, which I've also spoken about. And once that primary antibody, the non-specific binding has been cleared, and what you have on your membrane is your protein of interest bound to a primary antibody, you then want to try and detect that signal with a secondary antibody. So there are two main factors that you should be considering when choosing your secondary antibody. So firstly, your secondary antibody must understandably be raised against the host of your primary. So for example, if you chose one of Proteintech's monoclonal antibodies, typically they would be raised in a mouse. So your secondary should be an anti-mouse IgG antibody. Now just a note here, if you're not aware, you can actually multiplex different mouse monoclonals because mice IgGs could be one of 4 different isotypes, and you can get specific isotype-specific secondary antibodies. So you can get a secondary antibody that binds to IgG1 or IgG2A, and you can differentiate between them. So just a note if you weren't aware of that. And then the second point that you should consider is actually the detection method that your lab is best set up for, in order to choose the right appropriate antibody conjugate. So that could be chemiluminescent, colorimetric, fluorescent, or radioactive. The most common conjugate is HRP, so that's horseradish peroxidase, and this catalyzes the oxidation of a substrate, such as ECL, to produce light that can be detected by an X-ray or a CCD camera. Running up behind that is the fluorescence detection method, which is increasingly being used to generate fluorescent Western blots, and these have a greater capacity to quantify your protein of interest. At this point, I just wanted to highlight the new product range that Proteintech are offering. So we've got the multi-Rab recombinant secondary antibodies, and they are conjugated to our range of Correlite Plus dyes for fluorescent detection, and of course HRP for traditional chemiluminescent detection. So these are precisely engineered recombinant monoclonal antibodies that actually recognize multiple complementary epitopes on the same IgG. So this product combines the high sensitivity of polyclonals, but with the superior specificity of monoclonals. So it's something to keep in mind if you weren't aware of these types of products. So like I said, the addition of a substrate such as ECL facilitates the signal detection of your protein on the membrane, and it will hopefully look something akin to this blot here. Now, one benefit of the Western blot technique is the ability to detect and quantify low abundant proteins in a sample, and that's really great for precious samples such as human patient tissue. But if you are looking to look at sort of femtogram level levels of protein, then certain adaptations need to happen. So one of those is to use a really highly sensitive substrate, like Proteintech Signal Bright. So on the slide here, I've highlighted the 3 substrates that you can apply. So that's Signal Bright Pro, Plus, and Max, and that will depend on how low your protein is expressed. Okie dokie, so I've now run through each step of the Western blot protocol, and I can now give you a few tips for optimization throughout. I'm now going to run through some of the advanced tips for the proteins that can be super tricky to work with, which I'm sure many of you may be working with. So if, like me, you study I used to study cell signaling, you will most likely be studying a phosphorylation state of your target. So I'm just going to talk you through some tips for using Western blots to detect phosphorylated proteins. So I know during my own PhD research, phosphorylated proteins, the Western blots I performed could be something of a nightmare. So hopefully I can help you with any issues that people might be having. So one thing that you should be really aware of when you're studying phosphoproteins is actually the specific phosphate group that your antibody is targeting. So some of your signaling proteins will have multiple sites of phosphorylation, and one might be more relevant to your research area than the other. So for example, I studied phosphorylated AKT during my research, and this protein has 2 important sites of phosphorylation. So it's got serine 473 and threonine 308. And these are both equally important in AKT activation, but actually evidence suggests that the serine 473 is more heavily involved in one signaling pathway over the other. So do be aware that different sites of phosphorylation can be cellularly and contextually different when you do choose your antibody. But during the actual Western blot, there are a few things that you can do to really make sure that that signal is as bright as possible. So during your lysis, like I've said before, always include a phosphatase and protease inhibitor. And we do recommend a cocktail of this. We also recommend that when you've prepared your lysis, your lysate solution, you quantitate it and then actually store it in a load-in buffer ASAP. So this is because the involvement of the reducing agent, so that beta-mercaptoethanol, can actually maintain the denatured state of both your protein, but also those phosphatases, those pesky phosphatases that can actually cleave the phosphate group before you have time to analyze it. Also, just keep everything on ice. So this reduces the catalysis of that phosphate group and means that your protein is not degraded in your sample. Also, because phosphate, the active state of your phosphate group is not always really abundant within your cell sample, what you can do is load more protein in case you can't actually see any signal on your Western blot. So just load a bit more and see if you can see it. And like I've also stated before, always use an antibody for a non-phosphorylated or total protein target. So it's really important to get that that comparison between the two. So moving on to smaller proteins with a molecular weight less than 20 kilodaltons, these proteins are more vulnerable to poor resolution and poor retention, but there are a few things that you can do to help this. So firstly, using an acrylamide-based stacking gel with a tris-trisine buffer system. So the difference in separation capabilities of a glycine and trisine gels is attributed to different properties of the glycine and trisine compounds. For example, their pK values and their ionic mobility. So trisine is actually more optimal for the separation of low molecular weight proteins because it stacks the proteins in a more uniform band, which means when they reach the resolving gel, they separate much better. And as you can see with this comparison of this Western blot, so on the left here, the sample was resolved with a trisine gel, and you can see these really nice clear bands of the low molecular weight proteins. But when you look at a glycine-based gel, actually they're all stacked and more difficult to resolve. So a lot of other issues that can happen with smaller proteins actually occur at the transfer step. So always check recommended settings on your machine for smaller proteins. So because overtransfer is essentially a really common mistake, as smaller proteins will migrate faster out of the gel and you risk them transferring eventually through the membrane and out the other side. So to prevent this, you can always use a PSQ membrane or a PVDF membrane with really small micropores, so 0.2 microns, which can help maintain those smaller proteins within the solid support. Also be aware that some proteins will escape the dye front prematurely. And so to stop this happening, you can soak your gel in an STS-free buffer or simply distilled water for 5 minutes prior to setting up a transfer. So this will help to equilibrate the proteins and wash away any residual STS, which makes the smaller proteins less likely to escape from the gel. And as a result, a higher percentage of your proteins, including the smaller ones, are retained and transferred to the membrane. So moving on to larger proteins. So during your STS page, your gel of choice should really be a tris acetate-based gel, and these tend to have a pH of 7. So tris acetate-based gels have a higher capacity for resolution than your standard tris glycine or bis-tris-based gels. They provide sort of a more open and less restrictive gel matrix structure compared to a tris glycine gel. And that allows larger proteins to migrate more effectively and separate from one another. So understandably, you'd also then use a tris acetate buffer system to accompany this gel. So usually non-gradient linear gels are best if you're looking at targeting a single protein, especially if it's larger. And you would also want to, like I said before, check the percentage acrylamide of your gel. So anything less than 8% would be good for proteins over 100 kilodaltons. But do be careful when you're working with a gel that is less than 8% acrylamide because they're super fragile. I know that there were countless ripped gels during my PhD research, which never leads to a good day. So in terms of the transfer of these larger proteins, like I said, you can always use a PVDF membrane, as these are better over nitrocellulose because they don't need methanol in the transfer buffer. So methanol is not ideal for larger proteins because it can actually make them precipitate, especially if these larger proteins are already prone to, dropping out of solution. So increasing the STS can also help in this respect. So increasing the STS concentration in your transfer buffer to 0.1% can ensure that your protein won't drop out of solution, it won't precipitate out, which is sort of the whole point. You want to keep those proteins as soluble as possible so that you can detect them. And again, as with smaller proteins, you should always use a membrane pore size that is most appropriate to your proteins. And here we recommend 0.45 microns so that your proteins have the highest chance of really embedding themselves in that solid support. So continuing with some transfer tips for larger proteins, use a wet transfer. That's always more efficient for larger proteins, and you can also always lengthen the transfer time. So you can do this overnight if you're really struggling and your sample, but always make sure to lower the voltage if you're doing an overnight transfer. So we recommend sort of approximately 40 milliamps in that regard. You can also use the molecular weight marker to assess the efficiency of your transfer. So looking at these high molecular weight proteins and making sure that those bands are really clear on your membrane. So moving on to our final part of the webinar today, we're now going to talk through the most common troubleshooting issues that time and again our technical support will hear from our researchers. So if you are at this workshop and you have never come across extra bands, then you are clearly a Western blot whiz, and I salute you. But I can hazard a guess that sort of 99% of you will have seen this problem before. Let me just see. So the bands that you will see above your protein target. So if this is your protein, your expected protein weight, that really dark band there. If you're seeing bands above it, just like I've highlighted here with the red box, these are most likely modifications to your protein of interest. So glycosylation is a big culprit that may catch people out and increase the band size that you're expecting. So even though glycosylation should theoretically only add around 10 kilodaltons to your molecular weight, it can sometimes appear a lot more than that on your gel. And this is because sugar groups can actually impact how well your protein denatures and how well that STS can coat your protein with that all-important negative charge. So you can add PNGase F to this for the N-linked oligosaccharides, and that works by cleaving off the glycosylation group, and hopefully that should get rid of any extra bands that can be attributed to glycosylation. On the point of post-translational modifications, phosphorylation can also affect the molecular weight of your protein. So just always be aware of what sort of post-translational modifications your protein can have on it, and just be aware that they might show up on your gel. Finally, the higher molecular weight bands could also be due to dimerization or oligomerization of higher order species. So this is often an overlooked reason for high molecular weight banding. So quite commonly you can see dimerization, so that's a dimer complex of your protein. Can also get tetramerization and also higher order species. So get your calculator out. If you've got loads of bands that are a lot higher, just see if there are multiple of your expected size. And what you can do there is just add some more reducing agents just to really make sure that your protein complexes are denatured. So moving on to the bands below your expected molecular weight, quite often these are branded as non-specific antibody binding and the antibody is sort of blamed. But actually these bands can represent differential isoforms of your target, and that can be, proteolysis, so cleaved portions of your protein. It can be alternative splicing, isoforms, or pre and pro forms of your protein. So it could actually represent your protein of interest, just in a different, unexpected format. So don't always blame your antibody. So many issues can also arise with lysates that you've been stored for a long period of time, especially if the lysates were prepared and mixed with sample buffer and boiled before storage. So protein integrity is usually at its highest in freshly prepared lysates with low levels of protein degradation and protein complex formation. But if the samples are stored for a long time, that increases the likelihood of protein degradation because of thermal cycling. So as you can see on the right here, I've shown a gel ran and freshly prepared samples compared to 5 years later, and you can see that these proteins are really degraded and blurred. So we do recommend using fresh lysate where possible, but obviously we know that that's not always possible. So if you can't use fresh lysates, just make sure that when you do prepare your lysate freshly, you aliquot into manageable aliquots. And you can store these at -80 long term or -20 for no longer than 3 months. So I've listed a summary here of some common troubleshooting issues that I've had, but that I haven't had time to sort of go through today. And just looking at the time, I probably don't have time to whiz through right now. So do take a look at this slide when we send out our follow-up email. And any questions, do feel free to reach out. So my take-home messages, this is one of my final slides, so you'll get to have your say in a minute. My take-home messages from this webinar are to optimize your lysis and sample preparation. So this is really crucial for any immunoassay, not just a Western, but as a Western protocol can potentially last a couple of days, you want to absolutely make sure that you get off on the right foot from the very beginning. Second point is to tailor your protocol to your protein of interest. So be protein specific. Look at the size, look at the protein translational modification status of your protein, and make sure that you are tailoring each step of your protocol to have the most appropriate equipment, reagents, and membrane for your protein of interest. And finally, I know when I was doing my PhD and running hundreds of Westerns a month, if the end result was terrible, my go-to reason would be, oh, the antibody doesn't work. But there's actually so much more to it than that. So from sample storage, gel components, just be careful just to optimize each step. So with that, I will stop talking. But if you want to learn any more, we have a video hub on our website. We've got all of the webinars that are recorded this week. We've got IHC, IF, immunoprecipitation workshops, and many more. So do feel free to check those out. We also have a lot of in-person events. So just have a look at our events link on our website to maybe meet us in person for some more Western blot advice. And I want to just use this opportunity to thank you all for attending. Because you've attended, you will receive a free antibody sample. If you follow the QR code link on the screen there, you'll get a certificate of attendance, and you'll get these slides and the recording of this webinar sent out to you within the next week or so. So with that, yeah, thank you for your time. I'll invite Ali back to join us now, and we're happy to answer any questions.
Thanks, Amy. That was a really fantastic webinar. Definitely learned some tips from you there. I just want to start by saying we've had a lot of questions in the chat about receiving the follow-up email and the slides. So we will send these all out by next Friday. I know you might not have received some from earlier in the week, but we are working on putting all that together. So by next Friday, definitely check your junk or spam folders. Unfortunately, emails can slip into there, especially when we send the different attachments and stuff. So definitely add us as one of your safe contacts and make sure you check those folders so you don't miss them there. But if you do find that you've still not received it, do reach out to us on the events at ptglab.com. I also had a question about an attendee at this event who is now interested in looking at the recordings from the other events, so we can definitely do that. So just reach out to us again at the events at ptglab.com and we can get you all the materials there to catch you up. So we had lots of really interesting questions, and we've got time to just go over a couple here. So let me see if I can do it in protocol order. Probably not as I read these out. But so we had one question about why it's important to use phosphatase inhibitors. So maybe, Amy, you could explain the difference between when you would use protease inhibitors, so all the time, versus when you would be definitely needing to use the phosphatase inhibitors in your lysate prep.
Yeah, so this is mainly if you're looking at a phosphorylated protein. So if you're a lot of researchers who are in cell signaling analysis, for example, when a protein is active, a lot of the time they'll be phosphorylated at specific sites, and if you're wanting to look at that phosphorylation status, you always want to put a phosphatase inhibitor in your lysis buffer, because a lot of the time these phosphatases will continue to work throughout your lysis, and what you don't want is that sort of activation status of your protein to be removed before you have a chance to perform your Western blot. So yes, always use protease inhibitors, and I would also always recommend doing phosphatase inhibitors as well for all of your proteins, but especially if you're looking at the cell signaling sort of style of protein, so looking at that phosphate group.
Great, definitely. Good advice. Okay, so we'll move away from the fossil questions. We had a few of those, which I have answered, and we can also follow up with answering anything we don't get round to in the session today. So we had actually had a lot of questions about recommended buffer recipes and also storage of different buffers. So including one question on whether how you might want to sterilize, say, your RIPA buffer if you're making that at home. So I would always recommend using something like a 0.22 micron filter. So pass it through a filter after it to sterilize it. Maybe store it for up to a month at 4 degrees, but really you want to be making as many solutions as possible fresh along the way, because you go to all this work to do your Western blot. You don't want to find out that your blot's all contaminated because there is something odd growing in the different buffers that you've had sat on the shelf for a long time. So that will just really keep your blots as clean as possible, which is definitely the aim of the game. Okay, we had another interesting question. This was just about some further clarification on what you mean by housekeeping gene or protein, sort of loading control for your experiment, and why that's important to include, and where you can maybe find good recommendations of what loading control to use for your protein of interest.
Yep. So a housekeeping gene, I might go back to that now. I'm not going to go back to my slide. It's probably a few clicks away. So a housekeeping protein is a protein, for example, actin, tubulin, GAPDH. These are proteins that if you change the cellular environment, they would hopefully remain consistent. So if you're looking at, for example, the knockdown of a protein of interest, for example, RAS, and you're wanting to look at the difference in RAS protein levels, you also want to keep a protein that isn't changed by the siRNA knockdown to compare your levels. So when you actually load your Western blot, you want a GAPDH, for example, will between samples hopefully remain the same banding level, the detection level in your signal. But if you were looking at the RAS protein, you would hopefully see a decrease between the knockout and the non-knocked out sample. So these are proteins that will remain consistent regardless of how you treat those cells. So they're really good to sort of look at relative abundance of your protein. I'm sure that there are websites that you can look at to find the most appropriate loading control for your protein of interest. What I would suggest is looking at what loading controls are best for your organelle of choice. So again, if you were looking at mitochondria markers, then use COX-4. If you're looking at I don't know, membrane proteins, for example, you might want to use actin because that's a structural protein. Callie, I'm not sure, do you know any resources that are potentially useful for this question?
Yeah, I think check the literature if anyone's done anything similar experiment to you before. And I mean, I would always recommend when you're doing your pilot experiments, just check if it's a new treatment type on your cell type or something like that. Make sure you're not seeing any variation in the expression levels of those proteins right at the beginning there. Test out a few to start with. I know we don't like doing that too much in the lab because it does mean there's a bit of additional work. Okay, here's another good question about how to decide between a wet transfer or a semi-dry transfer. So for this, I would always suggest if you're looking at anything kind of over 100 kilodaltons, you probably want to err on the wet transfer side. Saying that, I have transferred proteins myself with higher molecular weight than that. The wet transfer is gonna take longer, but it does give you a really efficient transfer. Certainly, if you're looking at those lower molecular weight proteins, you want to use a semi-dry transfer. You can often do quite a short transfer, so giving you the best chance to retain the proteins on the membrane. When it does come to semi-dry transfer, the manufacturer will always give their recommendations for the conditions to use and for what molecular which molecular weight of protein that you are trying to transfer there. And a lot of these are programmed with nice ranges, so you could transfer something at 30 and 120 kilodaltons quite easily at the same time there. Okay, I think we might have time for one more question, Amy, before we wrap up. So this was a good question. I think you covered the reasons for this at the end, but it's always nice to recap on a bit of a troubleshooting to finish off. So if you see if the protein of interest is seen at 2 different molecular weights on the membrane, and they have asked, could this be a problem with the antibody, which is always the first point of call, as you suggested, or another technical issue like gel size or voltage. And interestingly, they say that they actually see the same difference between their, let's say, control and treated group in these bands of the two different molecular weights.
Interesting. I don't think that that is an antibody issue. Correct me if I'm wrong, Callie. I think that that will be, if you're seeing it in both, then I think that that is probably different isoforms of your protein. Could be phosphorylation, could be dimerization. Have a look at the actual molecular weight of your secondary band. If it's double, it's probably a dimer. If it's or quadruple, it's going to be a tetramer. Look at the isoforms, look at the splice variants of your protein. So you can use resources like GenBank or SpliceVista or UniProt, I think also gives you the splice variants of your protein. That will give you the different sizes that your protein could actually appear in. So your antibody will be binding, if it's a polyclonal antibody, especially, if you've got splice variants, they will be binding to both, but both of those variants. So that will be why you're seeing a multiple band.
Great, yeah. I totally agree with the points you've made there. So I'm just checking the last few things coming in the chat here. And I would say that just any further questions or concerns you have about receiving the slides, if you received the link from someone else, just give us an email at the events@ptglab.com, and then we will then be able to send you the recording and slides directly there, because you won't be in our email list at the moment. But yeah, I'd like to say thank you for everyone for attending. Thank you, Amy, for such a fantastic webinar. And do get in touch, everyone, if you have any further questions.
Thanks for joining, everybody.